Good morning, guys. Today we are going to perform a single sideband experiment. As you know, in the previous class we have done double sideband. Okay, with the name easily you can identify the, there are two main differences here. Okay, double sideband and double sideband is two-sided band and single sideband is one-sided band. So what is oh, so what was the disadvantage of the double sideband? Because you need more transmitter and the more bandwidth required. Okay, that means twice the maximum frequency bandwidth was needed for the double sideband, where in the single sideband you need the half of the double sideband. Okay, so we prefer the single sideband modulation. So let us start the experiment. Okay, before starting the experiment, let us have a clear idea of about the double sideband. Okay, here you can see uh, in this part. Okay, this is the double sideband. Okay, upper sideband and the lower sideband. FC is the carrier frequency, and this is upper sideband and this is the lower sideband. Here you can see in the single sideband you can see only upper frequency here, wherein the lower frequencies are stopped. Okay, that means we are using suitable filter to just stop the lower frequencies and just allow the higher frequencies. Okay, so in the practical, so this is not impractical because here you cannot stop whole. Let me draw the filter response. Suppose I have some filter. Suppose this is my filter. Suppose this is my high pass filter. If I want to transmit some spectrum, okay, this is spectrum. Okay, so this is ideal filter. If it is an ideal filter, you will get the response like this, and whole your lower frequencies are stopped. Okay, and higher frequencies are allowed to pass. Wherein it is in the practical, it is very difficult to implement this ideal filter because we do not have the perfect edges, because we have a 90 degrees fall time and the rise time and the fall time. Okay, so you will get something like this response. So you will get something like this response. Okay, so this is the higher frequency. Okay, suppose you are let us take one more. Suppose this is the whole frequency you are transmitting, and here you will get something like this. Okay, so what is this? These are the lower frequency component which are not stopped, because you cannot it is impossible to implement the practical sorry, it is impossible to implement ideal filter. Okay, ideal filtering is nothing but perfect. This is the HPF for ideal. Okay, this is nothing but ideal response. Okay, this is ideal response. So we cannot have ideal filter. So this is our practical. So these frequencies are, this is the lower frequency component which is not passed, which is not stopped. So due to this we will get a component like this. Okay, so let us implement this in the practical. So this is the given circuit. This is this is carrier frequency, double sideband and single sideband. Okay, from output we are connecting to the single sideband. Okay, from and we are seeing the output of okay at y1 and single sideband output at y2. This is from the function generator output, from the function generator to the single sideband. Okay, from single sideband output to the y2, and then this board is common grounded. Okay, so output is connected like this. Okay, this is connected to the ground and y2. Okay, let us start the connection. Okay, so here AM light is glowing. Okay, this is AM we are working with the AM. Okay, from here output is connected to the single sideband. Okay, and from single sideband we are connecting to the Y1. Okay, okay. From output to the Y1. Okay. From output to the Y1, and from single sideband to the Y1. Okay, and output to the Y2, and output common is grounded. The board and the main board is grounded. Okay. So we are plotting the response. Okay, we are plotting the Bode plot to see the filter response here. Okay, so minimum frequency and maximum frequency we will set on the Bode plot at the plotter. Just put the experimental area. Okay, and just write the maximum and the minimum value. Here is the Bode plot. Okay, here you can see board. Okay, Bode plot. Here we can plot the response. Okay, just click the board and write the minimum frequency is 5000 here, and the maximum frequency is 25,000. Okay, just write 5000 hertz, and the maximum is 25,000. Okay, and in the steps of 40, and the maximum frequency has 12. Peak to peak, sorry, the peak value voltage is 12. Okay, let us plot it. So we will include the phase here, no need for phase. So it's working on it. Right. You can see here, slowly it is being plotted. As you can see here, now this is the response. Okay, so this is not the exact step, it is a just decaying. Okay, so just from here in between 8 and 100 11 kilohertz, we will just find out the some points, and we will take the frequency and the voltage over there in terms of dB. Okay, let us take in between. Okay, so here the frequency is 9822. Okay, 9.8 kilohertz, and that in the decibel it is minus 8.94. just tabulate this value. Okay, this is F1 and this is A1, suppose. Okay, let us write this value. F1 as 9.22. Okay, just magnitude over 2 kilohertz F2, and A1 value is 8.94 dB. Okay, let us write again F2. Okay, this one. Okay, click in between 11. Okay, anyway, so here it is 10 point so 10.8 kilohertz, and A2 is minus 3.21 dB. Okay, just put in the formula A2 minus A1 by log F2 minus F1. Don't see this value, these are for some other value. Just consider F1, F2. Okay, you will get some other values. Okay, so from here plot, okay, your response here. Okay, you will get something like this, and you are taking the two values here, just put in this formula e2 minus a1 by log f2 minus f1. So here you just write the value f1 f2 a1 a2. Just from here you can calculate the cutoff steepness. Okay, so here you will calculate the cutoff steepness. Based upon that, we will now we will perform the SSB spectrum. Okay, here you can see SSB spectrum. This is a circuit. Okay, so here this is output from the function generator is connected to double sideband. Okay, so from double sideband also we are checking the output of the double sideband and the output of single sideband, and we will compare. Okay, so what is the difference between two, how we are getting. Do the connection here from output to the double sideband. Okay, from double sideband and single sideband we shorted from the single double sideband to y1 and output to the y2, and this. Okay, connected to y1 and output also connected to y2. Okay, single, we are checking the output at the double sideband and single sideband. Okay, like this. So let us keep this. Okay, keep these parameters to peak to peak 1 kilohertz and this is 0. Yes, go and set the parameter in the function generator. Open the function generator. Okay, let us set the parameters to peak to peak 1 kilohertz and DC as 0. So it is. Okay, now let us take the spectrum. See, here you can see you are getting the carrier frequency at 10 kilohertz. Okay, because here x per division is 10 micro. Okay, if we change this x per division and the curve y2, so we have to make it dual. Okay, dual, because we are checking input and output both at a time. Okay, so here when you take dual or y1 at a time, you will get y1, okay, as double sideband and y2 as single sideband. Okay, so before that you have to set this parameter to 500 micro. Okay, when you make in the function, when you set the function generator properly, so 200 micro or 5, okay, let us make it 500. Okay, just draw this two spectrum. y1 is nothing but the output of double sideband. Okay, the output of double sideband is the y1. Okay, from here you can see y1 is nothing but output of double sideband. So you are getting two bands here, upper and the lower. Okay, so here the frequency in between the frequency is 11, sorry, 9, 8, 9 and 10. Here the upper sideband is at 11. So here you can easily see that this is a double sideband. Okay, so it is double sideband, so with the y1 at y1. Okay, at y1 it is double sideband. At y2, let us check. Okay, let us take a single shot here. Okay, so here you can see this is single sideband, but actually the thing, it should be, you should get only one upper sideband, but here this lower sideband with the less amplitude you are getting. Why? Because this, as we draw here. Okay, if I want to okay, suppose this is the two band we are transmitting. Okay, and that is everything. Okay, actually this is double sideband. Okay, so frequency here it is 9 and 11. So wherein here it is less amplitude and this is okay. Why? Because you are not get the output was filter output was like this. Okay, so because of this sharpness, cutoff sharpness, actually the filter response should be like this, higher upper side, sorry, for high pass filter HPF, this should be the response. It is ideal, so we cannot implement ideal. So this is the practical filter. Because of this, we are getting the lower side band. Okay, so here this is the lower side band. Okay, with the less amplitude because of the cutoff sharpness. You see, because of this, okay, because of this, here you are getting a high frequency component here, but due to this low frequency component also available. Understood? This is the single sideband modulation. So this is this component. Okay, so here we conclude our single sideband modulation. You can plot your output here. Okay, it will be something like this in between. So this is here, it will be here just like this. At this point you will get around 9. Okay, around 11, you will get like this. Okay, this is double sideband. Okay, so single sideband will be at 9, you will get small component. Okay, at 11 you will get higher component. This is at 9 and this is at 11. Okay, this is single sideband. Okay, so this you can draw and write the conclusion here. So let me just write the value for you. What was F1 here? We can write F1 as F1 is 9.822 hertz, and F2 is, sorry, A1 is minus 8.94 dB. Okay, and F2 is 108.66 hertz, and A2 is minus 3.21 dB. Okay, you can plot it like this. Okay, exact, not properly. Okay, you can draw, it will be something like this here. Okay, just a rough sketch. Okay, just put the values here, you can evaluate it. Okay, hence here we conclude experiment 2, single sideband modulation. Thanks for watching. If you have any doubt, you can write email or course message. Thanks for watching. Have a good day.